Have you ever run into an integral that standard methods just can't seem to touch? Consider this one, the integral from negative infinity to positive infinity of 1 over x squared plus 1 squared. Normally, we reach for our trusty calculus toolbox, u substitution, integration by parts, or partial fractions. But here, those methods hit a wall. They struggle to handle the combination of the squared denominator and the infinite bounds effectively. It is a true calculus roadblock. When standard methods fail, we need a new perspective. There is a powerful shortcut waiting for us in the complex plane, using the residue theorem to bypass this roadblock entirely. Calculus often limits us to the flat real number line. But what happens when our equations hit a dead end? We shift our perspective to the two-dimensional complex plane. Imagine the real line as just one part of a much larger map. Now, we can bend the real line into a closed contour. This is not just a trick. It allows us to find hidden paths around mathematical obstacles known as poles. By bypassing these points, we turn impossible real axis problems into elegant, solvable complex integrals. The first step is to take our real function, which depends on a single real variable x. To move into the complex plane, we substitute the real variable x with the complex variable z, defined as x plus I times y. This gives us our complex function, f of z. By extending the domain to the complex plane, we gain the ability to navigate around singularities. To solve these integrals, we need to extend our view into the complex plane. We start with a path on the real axis from minus r to r. By adding a giant semicircular arc in the upper half plane, we create a closed loop known as a contour. This contour encloses the region of interest, allowing us to use Cauchy's techniques to evaluate our integral. In complex analysis, poles are the specific points where our function blows up, where its value approaches infinity. These points are where the denominator of our function equals 0. To find these obstacles, we isolate the denominator q of z and set it equal to 0. Solving this equation reveals the coordinates of our poles in the complex plane. Consider this example. Where is the denominator 0? Solving z squared plus 1 equals 0 gives us poles at positive I and negative I. These points are the secrets to the entire problem. By locating these poles, we know exactly where our function behaves strangely, allowing us to build our path around them. Not all singularities are created equal. In complex analysis, we call these points poles, where our function's value shoots to infinity. A simple pole occurs when the denominator is 0 to the first power. It's the most straightforward case to solve. When the factor is raised to a higher power, like 2, we have a higher order pole. This requires a more complex residue formula involving derivatives. Identifying the order of a pole is your roadmap. It tells you exactly which residue formula to apply to find your answer. A residue is the measure of the strength or influence a pole has on the surrounding complex space. Think of it as the mathematical key that unlocks the value of an integral around that specific singularity. By winding a contour path around the pole, we capture its unique contribution to the function's global behavior. This value is the residue, and it is fundamental to solving complex problems with elegance and efficiency. To find the residue at a simple pole, we use this elegant limit formula. It essentially mutes the part of the function that blows up at that point, allowing us to see the constant value left behind. When we multiply our function by the term that creates the pole, the singularity vanishes. For this simple case, we are left with the value of 1. This constant value is our residue. It represents the strength of the function's behavior at that specific pole. Remember, the residue acts like a localized fingerprint of the function near the singularity. Sometimes a pole isn't just a simple point where a function blows up. When a function approaches infinity faster, we call it a pole of order n. To find the residue here, we need a special formula. This looks intimidating, but it is very systematic. First, we multiply by the term that creates the pole to cancel it out. Then we take the derivative n-1 times. Think of the pole as a stronger singularity. Where a simple pole is like a mountain peak, a higher order pole is much steeper. This derivative process allows us to extract the specific residue weight hidden within that steepness. The process is always the same. Identify the order, apply the formula, and solve. It's a powerful tool that brings order to even the most complex singular points. Cauchy's residue theorem is the final piece of our puzzle. It elegantly states that the contour integral of a function is simply 2 pi I times the sum of the residues enclosed within our path. By identifying the residues at each pole inside our contour, we convert a complex integration problem into a simple summation of values. This is the moment where the hard calculus disappears, leaving us with a straightforward algebraic result. It is a powerful bridge between geometry and algebra. Now that we have our residues calculated, we arrive at the most elegant part of the process. We use the Cauchy Residue Theorem to link our contour integral to these residues. We take every individual residue we found inside our contour and we add them all together. This sum represents the total influence of the singularities enclosed within our path. Finally, we multiply that entire sum by 2 pi I. This simple multiplication collapses the complexity of the entire path integral into one final, clean numerical result. It is truly remarkable how a complex, winding path integral can be solved with just this simple algebraic step. We are tackling the classic integral of 1 over x squared plus 1. Standard methods work, but let's see how the residue theorem handles it. First, we promote this to a complex function f of z equal to 1 over z squared plus 1. We map this onto the complex plane to identify where the function becomes undefined, the poles. The function blows up at z equals I and z equals negative I. These are our poles. We choose a semicircular contour that stays in the upper half plane. Notice it encloses only the pole at z equals I. Because our contour only captures the pole at I, we can ignore the pole at negative I, making the math much simpler. Now we focus on the poles of our function. Looking at our complex plane, we have two singularities, one at positive I and one at negative I. We are using an upper half-plane contour, which means we only care about poles located above the real axis. The pole at negative I sits outside our region, so we simply ignore it. To find the residue at z equals I, we multiply our function by the term z minus I and take the limit as z approaches I. After simplifying, the residue is 1 divided by 2I. We have found the residue at our pole I to be 1 divided by 2I. Now we apply Cauchy's residue theorem, which states the integral equals 2 pi I times the sum of our residues. Substituting our residue into the formula gives us 2 pi I multiplied by 1 over 2I. Watch closely as the imaginary unit I cancels out, along with the factor of 2. We are left with a simple, elegant result, pi. What once seemed like a daunting calculus problem has effectively solved itself through the power of residues. Modern computational tools like SymPy or Mathematica have changed the game. They can identify poles in complex functions in a fraction of a second. While these tools automate the heavy lifting, they shouldn't replace your intuition. Your role is to verify the paths they choose. Always treat AI as a powerful assistant. Understanding the underlying theory ensures that you catch errors and interpret complex results with confidence. Mathematics often feels like a series of abstract formulas, but in complex analysis, geometry tells a much clearer story. When we use the residue theorem, we aren't just calculating a value. We are analyzing how a path or contour winds around a singularity, which we call a pole. Notice how the path effectively encloses the point where our function becomes undefined. This winding motion is the heart of the residue theorem. By visualizing this, abstract algebra becomes a concrete image. You are seeing the influence of the pole on the surrounding space. Remember, whenever you see an integral, think of the geometry. It's the path taken that reveals the hidden value inside. Even experienced mathematicians make mistakes. The first classic trap is simply forgetting the 2 pi I factor in Cauchy's theorem. Next, always be careful with pole order. A simple pole and a higher order pole require different limit formulas. Don't mix them up. Finally, always check which poles actually sit inside your contour. A pole outside the path contributes absolutely nothing to the integral. Double-check your factor, verify your pole order, and confirm your contour boundaries. Accuracy is the secret to complex integration. Why do we use the residue theorem? It is all about efficiency. Finding an analytical shortcut is significantly faster and requires far less power than forcing a computer to brute force a numerical approximation. Numerical methods must discretize space, checking millions of points one by one. This demands massive computational resources. In contrast, the residue theorem gives us a direct, elegant analytical path. We simply circle the pole, calculate the residue, and arrive at the result. This isn't just theory. As this chart shows, the analytical approach drastically reduces the computational workload. Less effort for the machine means more focus on solving the actual problem. By embracing the residue theorem, we trade raw, expensive processing power for mathematical elegance and efficiency. You have now mastered the most powerful bridge in complex analysis. Let's look back at the workflow that allows us to solve the seemingly impossible. By identifying poles, calculating residues, and applying the Cauchy theorem, you transform complex problems into a simple multiplication. The residue theorem is your bridge to solving the impossible. Rigorous, elegant, and efficient, you now have a framework to handle any complex integral that comes your way.